Welcome back. In these next few videos, we'll talk about some methods that we can use to find functions or find the distribution of functions of random variables. So we'll start today with the method of distribution functions. First, we'll lay out a big assumption going forward. After we lay out that big assumption, we'll talk about what we mean by transformations and why we might care, before finally introducing the method of distribution functions as our first way for finding a transformation. So one of the primary goals of statistics is to make inferences about a population based on information contained in a sample from that population. Now, as we've been sort of hinting at all semester, probability theory is really the toolbox that's required to do that. So in statistics, what we're really thinking about, or what we're really saying, is that all of the quantities that we're using to estimate these population parameters are just simply functions of n observations or n random observations from a sample. So what we're truly looking at is a series of n random variables collected from a population. Now, we'll assume throughout the rest of the class and beyond, so even further when we talk about some techniques, that populations are relatively large compared to the sample size. As a consequence, what this means for us is that we'll assume that these observations are independent of one another. Now, in practice, that might not always be a reasonable assumption, but whenever it makes sense to assume that our data are independent, we tend to do so. The reason for that? We don't have to worry about covariance. We don't have to worry about correlation. So in this independence case, we say that the joint probability function in the discrete case is the product of the probability mass functions. In the continuous case, the product of the probability density functions. So we can get a joint probability function for up to n random variables. The statement that we'll make throughout the semester to really shorten this assumption is that y1 through yn is a random sample from a population with density f of y or with mass function p of y. This means that the random variables are independent and have a common density function. So they're independent and identically distributed. So there are three major methods that we can use to help us find the probability distribution of some function of random variables. So maybe we know the distribution of y, but we'd like to find the distribution of y squared, or the natural log of y. These methods are the method of distribution functions. As you might guess, that's based on working with the CDF, or the cumulative distribution function. A second method called the method of transformations, and then the method of moment generating functions. So in this video, we'll focus on the method of distribution functions. In later videos, we'll talk about the method of transformations and the method of moment generating functions, or MGFs. Multiple methods may apply in the same scenario. However, it usually turns out that one method is easier than the rest. So for example, if we're interested in finding the distribution of a linear function of random variables, say y1 plus y2 all the way up to yn, this third method, the method of moment generating functions, turns out to be quite a bit easier. If we have a monotone, so non-increasing, non-decreasing function, the method of transformations is really a fantastic shortcut. The most general of these three methods is the method of distribution functions. So that's the one we'll start with. Here's how the method of distribution functions works. So we'll let u be a function of the random variables y1 through yn. First, we'll find the region in the u space that corresponds to the y1 through yn space. So what does u equal u translate to in terms of the y's, in other words? We'll then figure out what region or what corresponds to the region u less than or equal to little u. We'll then find the CDF of u, f of u, by integrating this over the region in terms of the y's, where u is less than or equal to u. So we'll essentially try to find a mapping from the y space to the u space. Then once we have the CDF big F of u, We can find the density function little f by finding the derivative, and that's how we'll get our distribution. So this method is most useful when we have continuous y's. We can certainly apply it in the discrete case, but then we have sums, and those tend to be a little bit trickier to work with. So let's take a look at an example. We have a process for refining sugar that yields or that produces up to 1 ton of pure sugar per day. The actual amount produced is a random variable because we have machine breakdowns, we have slowdowns, so we won't always reach that time. Suppose that y has distribution function given by 2y for 0 less than or equal to y less than or equal to 1. The company is being paid at the rate of $300 per ton for the refined sugar, but we also have some fixed overhead cost of $100 per day. So in terms of the daily profit, we'll define a new random variable y like, or a new random variable u, like this. U is 3 times the amount that is produced, so 3 times y, minus the fixed overhead of 1. So u is essentially in hundreds of dollars. Let's find the probability density function now for u. So this is a great example of a transformation that we might be interested in. So let's start by writing the probability that u is less than or equal to little u in terms of the CDF of y. So the CDF of u is the probability that u is less than or equal to little u, which is the same as the probability that 3y minus 1 is less than or equal to little u, which in terms of the random variable y looks like this. It's the same as the probability that y is less than or equal to u plus 1 over 3. So now we can integrate this to find the CDF of u by integrating the PDF of y with respect to y over this new range that we've generated. So from 0 to u plus 1 over 3. So then this gives us y squared evaluated from u plus 1 over 3 to 0. So we get u plus 1 over 3 for our probability that y is less than or equal to u plus 1 over 3, which is in fact the CDF of u. So here we go. We've got our CDF now. This isn't defined everywhere. So the other thing we need to consider, how do the bounds of y map to the bounds of u? So y is defined from 0 to 1. Since u is equal to 3y minus 1, that means that u starts at -1, runs up to 2. So that's our range for the daily profit. We'll then take the CDF here to get the PDF. So our PDF, or our density function of u, is 2/9 times the quantity u plus 1. So that's the method of distribution functions. Now, in the bivariate situation, we can still apply this. It just becomes a little bit trickier to work with. So y1 and y2 are random variables with a joint density function. U is then a function of y1 and y2. So then for every point y1 and y2, there's only one corresponding value of u. So we just have to find the region of values where u is less than or equal to little u. So for example, we'll let y1 and y2 denote a random sample of size 2 from the uniform distribution. Let's find the density function for u, which is the sum of those uniform random variables. So the hardest part of this problem is actually finding the limits of integration. Once we've got that, it's fairly straightforward to integrate. So let's start by finding the joint density function of y1 and y2. We will need that to solve this problem. Because we're assuming y1 and y2 are independent, we'll take the product of their PDFs. Because these are both uniform random variables from 0 to 1, their PDFs are 1, so we take their product, we get 1 for the joint PDF. So our joint PDF is 1 for y1 between 0 and 1, and y2 between 0 and 1. In order to find the CDF, we need to know what values of u map to values of y1 and y2. So our CDF of u is the probability that y1 plus y2 is less than some value little u. So that's the region that we'll want to integrate over. But what does this look like? Well, it looks like this. So we have y1 on the x-axis, y2 on the y-axis. Both range from 0 to 1. So think of this square as the y-domain. Each pair of points that we add together will generate a horizontal line, a diagonal line. So these diagonal lines are going to represent different values that we can reach of u. So we've actually got two regions that we need to think about because our u is defined as sort of a diagonal line. If u is between 0 and 1, then that means that we're somewhere in this lower triangular region. If u is between 0 and 2, however, such as over here, that means that we have more of a trapezoid to integrate over. So the bounds are going to be a little bit more difficult. Let's start with the simpler case. Let's start with u less than or equal to 1. So in that region, our bounds look like this. y1 is going to range from 0 to u minus y2 because we're just rewriting that, solving for y1. We've integrated out y1 in the second integral, so y2 now goes from 0 to u. Solving that through, we get a CDF of u squared over 2. This one's a little bit harder, and I recommend taking the complement approach to this. So let's go back and look at what this PDF or what this area looks like. We've got two choices here. For u, between 1 and 2, we can either integrate over this gray trapezoidal region, or we can take 1 minus this triangle up here. Integrating over this triangular region is going to be much simpler. I would recommend taking that complement rule-based approach. So our CDF of u is going to be 1 minus, this is the integral over that triangle. A little bit of algebra, we get something that looks like this. Negative u squared over 2 plus 2u minus 1. Now we'll combine in both parts to get the CDF. So the CDF will have multiple parts here as well. We'll take the derivative of each of those parts to get the PDF. So here is our final PDF. The probability density function that u is equal to some value is u from 0 to 1, 2 minus u from 1 to 2. Now, this can also be used, of course, to find the distribution of a single random variable y. So let's take a look at this transformation. We have we have y with PDF y plus 1 over 2 for y between negative 1 and positive 1. We'd like to find the density function of y squared. Well, the bounds on y squared are going to be a little different. Y squared is going to range from 0 to 1. How are we going to work with that? How are we going to find this? So the CDF of u is the probability that big U is less than or equal to little u. So the probability that y squared is less than or equal to u. We have really two ways that can happen. So y squared is less than or equal to u if it is between negative square root of u and positive square root of u. So y can be negative, y can be positive here. So we'll integrate this from negative square root of u to positive square root of u. There's our PDF, y plus 1 over 2. We end up getting something that looks a little bit like this. After some algebra, we get that the CDF of u is the square root of u. Take the derivative. Here's our PDF of u. 1 over 2 times square root of u for 0 less than u less than or equal to 1. Now, this method of distribution functions, in most cases, is not the easiest method. It's time-consuming to figure out where that mapping of y to u lays, especially in the multivariate case. We have a lot of integration, we have derivatives. It's a Calc 2 student's nightmare. It is the most general method, which means that it applies in the most cases. In the next video, we'll look at a method called the method of transformations, which is a little bit easier, but it applies in fewer situations. I'll see you then.